Live streaming. You might have to click like OK on there a couple times. Forward to the cloud. Yeah. And without further ado, all right, it is fall 2024, and we are in our 103rd semester of the Water, Wetlands, and Watersheds Seminar, because it was started in 1973, so it's 51 years. Is it our 101st?
You say 102nd.
It's our 102nd semester of the Water, Wetlands, and Watershed Seminar. So thank you all for joining us, and thanks to our first speaker of the semester. So Dr. Emma Mackey. Okay, so Nikki Mackay. She's an assistant professor in the geological sciences here at the University of Florida. She has her undergraduate from Harvard University and got her PhD from Stanford in 2021, after which she began here as an assistant professor. She and her Gator Glaciology lab focus on investigating the conditions below glaciers and ice sheets and their influence on how ice sheets evolve and change over time. They specialize in the development and application of machine learning tools. She won the AI Rising Star Award recently, which came with a trophy and no money. Apparently, like not even like a gift certificate for lunch or anything. Okay, so congratulations. But we'll see today that areas of Dr. Mackay's research include geophysical data analysis, geostatistical simulation, hydrological modeling, and geologic interpretation. So with that, I'm going to hide all this so you don't have to look at it.
All right.
And meeting controls. And you should be good to go now.
Thank you. Well, thanks for having me here to talk about my wetland of sorts. I'm going to be talking about the subglacial landscape, which includes a very complex hydrological and geological environment. I know you all probably think more about water than rocks, but I'm going to talk a little bit about the geology as well, because those two are so geophysically intertwined. The Gator Glaciology Lab right now is made up of 3 PhD students, Michelle, Michael, and Mia, and a bunch of undergrads. Nate recently graduated and has stuck around as a lab tech. So good bunch of students coming from all sorts of disciplines and departments. Many people ask me why I'm studying glaciers here in Florida. And the honest answer is that I got a tenure track job, but what I tell everyone is that we have more to lose than any other state when it comes to sea level rise and changes at our ice sheets. So it is important that we are thinking about what's happening at the poles of Florida. Many of you have probably seen this IPCC chart showing sea level rise trajectories over the next century. There's a lot of uncertainty, partly because of uncertainties in model parameters and unknowns and what our future carbon emissions are going to look like. I also want to highlight this dashed line, which is the low likelihood but high impact scenario that could maybe possibly unfold due to ice sheet instabilities, which are different ice sheet processes and positive feedback loops that could unfold and lead to unmitigated retreat if we hit certain tipping points in our ice sheets. So it is very important that we are investigating those ice sheet processes and conditions in order to be able to reduce, but also better quantify that uncertainty there, because that uncertainty envelope is very important for decision making here in Florida. We want to make sure that our nuclear power plants are not built to the 50th percentile risk scenarios, but to those higher ones. So a big part of the unknowns and uncertainties in ice sheet processes comes from the subglacial landscape. So the subglacial environment includes complex topography. We have geological changes, we have soft sediment or hard crystalline bedrock. There is a lot of subglacial water in both Greenland and Antarctica. So the base of the ice sheet is actually relatively warm compared to the surface because the ice sheet acts as a big insulator. We have geothermal heat flux underneath the ice that can add a little heating. The ice can be up to 4 kilometers thick, which is a lot of weight to put on the bed, and that reduces the melting point of water. The ice moves through a combination of internal deformation and sliding over the bed, and that sliding can also create frictional heating. And then more in Greenland than Antarctica, but you can have a lot of melt being generated at the surface that then percolates down into the bed. So through all of these different mechanisms, we have a ton of meltwater at the base of the ice sheet. This melt has an effect on the friction at the ice bed interface and influences how the ice slides, along with the geology and the shape of the topography. So ice flows at different speeds over different interfaces. There are also a lot of complex geological processes that redistribute the sediment and material underneath the ice and can lead to the development of these, different morphological features, which can also have different effects on ice sheet stability. Of course, this environment is super difficult to study because the ice sheets are massive, they're really thick, it's cold, it's hard to get to. And then we have to somehow try and see through this to characterize what that landscape looks like at very high resolution. We rely mostly on geophysical observations. So I'm not a geologist, I'm a geophysicist. That means I rely on indirect measurements like radar and remote sensing, seismics, and then gravity and magnetic data. So the radar and gravity and magnetics are usually airborne. These sensors are mounted on aircraft and flown across the continent. Seismics are much more labor intensive because you have to physically go out there and set off dynamite or otherwise create vibrations. So we have different types of information at different spatial scales and resolution, and they're sensitive to different aspects of the glacier and the terrain beneath it. And so we need to use those things to create a more complete image of the subglacial landscape. But this is still really hard to do at the necessary scales and resolutions for ice. One of the really important things that we do with our radar measurements is measure the ice thickness and the shape of the topography underneath the ice. So that figure shows bed elevation measurements from airborne ice penetrating radar. So the radar can see through the ice. Ice is dielectrically very similar to air, and then it reflects off the bed topography, and we can measure what that looks like. Those then have to be interpolated to construct these more continuous maps of the topography that then gets fed into ice sheet and sea level rise models. Problem is, there are a lot of gaps in these measurements. A couple of these biggest ones were just recently filled in, but we still have tens of kilometers of gaps in measurements. And these gaps are interpolated in a way that creates a lot of smoothing. So this is a spot in East Antarctica where the slope of the bed is effectively zero for an area about the size of Florida. I know Florida is actually that flat, but East Antarctica is very mountainous. And this is a problem because it means that we have unrealistically smooth information going into our ice sheet models. And the ice is going to behave very differently on the surface like that than it would over a mountain. So how do we actually initialize our ice sheet models if we don't know the basal parameters? Well, ice sheet models are tuned in a very complex way. We need to know what our physics is, our topography, some sort of ice rheology or deformability of our ice, and then what the friction is at the bed. So those are like the key ingredients to run an ice sheet model. But these are all really hard to know. We still don't know the governing physics of how ice slides. We have a lot of different hypotheses, but it's really difficult to test those when we also don't know the other input parameters into our model. So to run an ice sheet model, what we do is we start with some smooth topography, and we pick some governing physics or sliding law. And then we use those two things to do an inversion for the ice rheology. So basically they tune, our ice sheet modelers tune our ice rheology parameters so that when you put that parameter into an ice sheet model, everything kind of makes sense and matches satellite observations of the surface elevation and ice velocity. So, this is kind of a tuning parameter. And then they take all of those things and do another inversion for basal friction. So basically, we are using ice sheet models to tune the parameters that then go into our ice sheet models, and then use those to make sea level rise projections. Obviously, that's really problematic. You shouldn't use your models to determine your model parameters and then make very societally impactful decisions based on that. The other thing I don't like about this is that there's no geological information going into this. Obviously, we don't have a complete picture of the geology, but the little information we have is completely absent from this process. So there's no geological realism going into this. The other thing I want to highlight is I made this biplot, which plots the principal components of different parameters against each other. And this is, on this axis is the friction coefficient of Antarctica that somebody made in this ice sheet modeling version. And then the other variables are the bed elevation, the topographic roughness, estimated temperature, and geology of Antarctica. Basically, if two variables were strongly correlated, they would be parallel on a biplot and orthogonal if they're uncorrelated. And what we're seeing is that none of these kind of geological variables are very strongly correlated with the friction coefficient. So this friction coefficient, which is this model parameter that's designed to represent geological processes, is almost like uncorrelated with any observable we have of the bed. So that's also really troubling to me. So we need to more strongly couple our knowledge of the bed with our ice sheet models. So yeah, we have this fundamental problem where ice sheet models lack geological realism. The topography textures are off and there's no geologic information going into this. So one important way that that my group is working to add geological realism to ice sheet models is through geostatistical simulation of subglacial topography. So here I've got some exposed ice-free topography in Greenland, where I pulled out some lines of data to represent like a flight line or radar survey that measures the topography. And then I interpolated it using kriging, which is a very widely used interpolation method. And you can see that this kriging estimate is much smoother than the true thing. And that's the kind of thing that people rely on. It's smooth, it's got these weird bullseye artifacts. On the other hand, we can use geostatistical simulation to stochastically simulate these measurements. And the idea behind geostatistical simulation is that your goal is to reproduce the variability or the spatial statistics in observations. So while kriging optimizes local accuracy, geostatistical simulation replicates the spatial statistics. It exactly matches any measurements that you do have. And you can generate multiple realizations which quantify your uncertainty. So you can think of this as like a profile here where we have these blue dots that represent measurements of your bed elevation. A kriging interpolation would look something like this red line, which, again, the objective is accuracy. And then each of these black lines represents a possible geostatistical simulation of the topography. So you end up with an ensemble. You can see that it quantifies your uncertainty. And each of these is realistically rough. And so it better captures the nature of the subglacial landscape. People often ask me, okay, which one do you use? And the answer is you use all of them. You don't pick one. The goal is that eventually people will be running ice sheet models with every single one of these so that we can then quantify uncertainty in our ice sheet models with respect to the uncertainty in the subglacial landscape, which we know is the dominating source of uncertainty. So I'm going to talk mostly about how we can use geostatistical simulation combined with other geophysical observations and methods to better map our subglacial landscape and use that to better understand the subglacial hydrology, ice sheet physics, and make ice sheet projections. So this is a wetland seminar, so I want to talk about water. This figure is from data at the top of the Greenland ice sheet, showing seasonal melt and then ice velocity at that location. And there's a clear link between ice velocity and melt production, which makes sense. As water is melting, it reduces the friction. So that's surface melt. Once melt hits the water, or hits the topography at the base of the ice sheet, it's really difficult to figure out where it's going. Subglacial water, much like rivers at the surface, are routed by the topography under the ice. So knowing the topography is very important for figuring out where the water is going and how that relates to ice sheet movement. So this is a model of the subglacial hydrology under the ice here. But without really knowing what our topography, it's hard to really pin down where those channels should be. This is just a figure or a picture I took at the top of the Greenland ice sheet, showing this, the top of this massive waterfall that goes through the ice. So the ice here is about 1,500 meters thick, and you're looking at the top of a plunge down, and this is so loud. This is just an incredible amount of water that's being delivered to the base of the ice at any given moment. This is also me in my tent. We had to move our tents every few days because the surface was melting so quickly that after a few days, the edges of your tent would start dropping down and the ceiling of your tent would get closer and closer to your face and get really difficult to kind of wiggle yourself into the tent. So this is about like 5 days worth of melt. It's not scientific, but you can definitely see a few inches per day here. So this is just an incredible amount of water. But without understanding where it's going under the ice, it's hard to say like how that matters. So what I did was generate geostatistical simulations of the topography. This is Jakobshavn Glacier in Western Greenland. It's the glacier that most likely generated the iceberg that sank the Titanic. And these are some bed elevation measurements in that area. So these are example geostatistical simulations of that topography. Bed machine is like the kind of existing state-of-the-art smoothed product that everyone uses, and these are some simulations for comparison with much more realistic topography. And then these are models of the subglacial hydrology for each of those. And I've highlighted some key differences here. Obviously, this main channel is reproduced across each realization, but some of these other channels end up in different places. So we can figure out which channels we have a lot of confidence in and which ones are more uncertain. Though this is just an average across them and then inverted. So this is 250 hydrological models stacked on top of each other. And we can see, yeah, big confidence in the main channel, but a lot of ambiguity in other places. So information like this is very useful for better understanding the hydrology and how that impacts the ice itself. Okay, so we have a lot of flowing water under the ice, but we also have stored water in the form of subglacial lakes. These dots here are known subglacial lakes across Antarctica. The blue ones have been identified by radar measurements, and then the red ones are active lakes, which are inferred from elevation changes in the surface of the ice sheet that people think are filling and draining subglacial lakes. Subglacial lakes are really important because they reduce the friction between the ice and bed. So we can see this lake here in the radar. It's very strong because water is very reflective to radar, so we get this very flat, bright interface. We can't see the bottom of the lakes because radar doesn't penetrate through water. Lakes probably also have very valuable sedimentary records that could tell us about the history of the ice sheets and are important targets for subglacial drilling projects. They can also drain suddenly, which has been linked to speed ups in ice velocity. And they may contain unique forms of life maybe or maybe not like that, that are analogous to possible life on other planets like Europa and Mars. For many reasons, we want to know where these subglacial lakes are, what their conditions are, and more about their dynamics. Curiously, we have these two types of lakes, the radar detected ones and the satellite altimetry detected ones. But strangely, we are not able to see the other type of lake with the other sensor. So these don't show up at all in the radar, and these have no changes in the surface. So the question is, why is that? What is different physically about these lakes? So I had a project where I was mapping these, and I also used geostatistically simulated topography in this. One of my colleagues has this like cryotunes Twitter where she makes cartoons of research. So this is from her. But basically, if you use really smooth topography, you're going to bias yourself towards bigger but fewer lakes. Whereas if you account for the roughness, then you get smaller, more numerous lakes. So this can give you a more accurate picture of what this subglacial landscape looks like. I use this to show that Antarctica probably has thousands of very tiny subglacial lakes, most of which haven't been discovered, and most of which probably are too small to be seen by radar. I also did some machine learning analysis to predict where you would be most likely to find these lakes. So this is showing where we would expect to see radar detected lakes in the dark blue areas. And then this is where we would expect to see these active altimetry detected lakes. And I found that the radar detected lakes are more strongly associated with really thick ice in the interior. So they most likely form through pressure melting. And the active lakes are more strongly correlated with high ice velocity conditions. So they're probably forming through frictional melt. And that also tells us a bit about why we don't see the other lake type with the other sensor. Radar detected lakes are in really slow moving stable parts of the ice sheet. So they're probably just not filling and draining. They've probably been sitting there for maybe hundreds of thousands of years. The active lakes are near the margins in super dynamic areas, parts of the ice sheet. So they're probably too unstable to develop that nice flat ice-water interface that gets picked up in the radar. So we can learn a little bit about this landscape. Yeah, so that's more about the hydrology. The other thing we can do with the simulated topography is better understand the ice sheet sliding physics itself, which is a big unknown in our models. This was a modeling study we did where we compared my simulated topography with some smooth topography. This is what everybody uses in an ice sheet model. And this layer is the ice sheet, and the colors represent deformation heating. So with a smooth bed, your ice basically flows like a block of ice. You've got this plug flow situation. And with the simulated topography, you end up with a lot more friction at the bed and deformation heating. And actually there's this shearing kind of at the top of the peaks here, where you get a lot of deformation at the base of the ice sheet. It's a lot warmer, geologically weaker, and maybe even this decoupling of this kind of basal ice with the main block of ice. So we're learning that ice behaves very differently on rough topography than smooth topography. So using this simulated topography, we can capture our ice flow physics much more realistically. In this region, we actually took boreholes in Greenland and found, and we're actually able to measure the temperature at the base of the ice sheet and found that the base of the ice is very warm relatively to the rest of the ice. So extra confirmation for this. So hopefully I've convinced you that we should be using geostatistics everywhere on our ice sheets. And I really want to. The problem is existing geostatistics software were really not up to this task. Geostatistics, at least advanced geostatistical simulation, has historically been most widely used in the oil and mineral exploration worlds. So the software was made by and for industry and exploration. They're very expensive. They often have their own like GUIs and tools that they use. And they're not designed for ice sheet scale problems with 100 million data points. So I quickly hit kind of a ceiling with what I was able to do with the software that existed. So I made my own Python software called Geostatsim. This is an example of some bed elevation measurements in Greenland and a lot of different ways to interpolate it using different geostatistical simulation or interpolation algorithms. And so this is in Python. It gets a couple hundred downloads per month. It's now being used in coursework all around the world, and we have users using this for glaciology, natural hazards, mineral exploration, even hydrology. So this is something that we're working on to make to serve as a more robust community tool that's open source. I also made a Jupyter book that introduces geostatistics and how to use these different methods in case you're curious. So yeah, this has been really nice, both for our own research, but also for teaching my students and helping these methods work their way into the community. One of the really annoying things about geostatistical simulation is that these algorithms are sequential. So let's say we have some cross-section of topography with some radar measurements. What we do is we pick some random grid cell location that we want to simulate, do a bunch of math, figure out some probability distribution of what the bed elevation could be at that given point. If we were doing kriging, we'd select the mean, but since we're doing simulation, we randomly sample from that distribution, and that becomes our simulated value. And then we go back to the beginning, pick a new grid cell location, do this again and account for this, newly simulated values so that we have this seamless interpolation of the topography. So it's sequential, which means that it's very slow. It scales exponentially when we want to do it for a big area. And gosh, I think it would take about a year to do one realization for all of Antarctica. Obviously that's not good. But one of my undergrads published a paper on a parallelization scheme for this, where we can actually use some tricks to do a bunch of math in parallel. So this is showing the reduction in runtime when parallelized across 12 CPU processors. And so now that it's parallelized, we're also working on making it run on GPUs. So this gets us a lot closer to being able to do this at ice sheet scales. And we're hoping to, right now we're adapting our Geostatsim software, or changing it to PyTorch and working in this parallelization so that it can run easily on CPUs and GPUs. So yeah, next up is a project I'm calling Demogorgon for digital elevation models of geostatistical origin, which would be making an ensemble of bed topographies for all of Antarctica that people can use for, as a basis for uncertainty quantification. I believe Demogorgon is also a Dungeons and Dragons monster. But anyways, we got funding for this through the HyperData AI and Complex Computational something award. So we're working with the HyperData technicians on optimizing our algorithms to run on GPUs so that we can hopefully do this in the next year and a half. There's a catch though. In the fast flowing areas of the ice sheet, we have to think about the principles of mass conservation. So when the ice is flowing, it to an extent expresses the shape of the topography beneath it. And, basically like what mass conservation says is that for any given column of ice flowing in has to equal ice flowing out. And if you violate that constraint, your ice sheet modelers will be very unhappy with me. So we have to interpolate our topography in such a way that mass is conserved. It's run. And so we can use the ice surface velocity and ice surface elevation to place some constraint on that topography. And that's done through an ice sheet or a mass conservation inversion. This is an ill-posed inversion, meaning that there are there's more unknowns than equations, and you have an infinite number of solutions to this problem. So people have solved this in the past by kind of smoothing out the topography and getting you a solution, but a very smooth one. But that's not what we want. We want geostatistically simulated topography that also somehow honors the physics. And we can do that through a Markov chain Monte Carlo framework. There's a lot of math behind it, but basically MCMC is just optimized brute forcing. And the idea is that you just iteratively perturb your parameters until you get it right. So we can do that with geostatistical simulation, and it's been done in the oil industry, where people geostatistically simulate some surface, compute your loss function, then erase a little bit of it, resimulate it, and then compute your loss function again, and then accept or reject that proposal sample based on the new loss function. And you can do that hundreds of thousands of times, run multiple chains, quantify your uncertainty, until you arrive at some solution. So again, we're simulating some topographies that matches our observations, computing our geophysical forward model or loss function, resimulating, recomputing the loss, and then accepting or rejecting, and then repeating that over and over again until some convergence threshold is achieved. So my student Nia is doing this for the mass conservation problem here in East Antarctica. This is the deepest land on Earth that's not ocean. That's a Denman Trough here. In Denman Trough, actually, the radar doesn't see this trough because the radar just bounces off the sides of it. But mass conservation tells us that there has to be a trough here, otherwise physics doesn't work. So, so this has previously been inferred through this very smooth mass conservation inversion process. If we do geostatistical simulation without any physical information, we can't see the trough, the radar. Nia has managed to combine both of these things, and we can get an ensemble of topographies that are both realistically rough and honor the physics and find the trough. So this is really great because now we can incorporate this realistically rough topography into ice sheet models and quantify our uncertainty. We're doing something very similar for mapping the bathymetry underneath ice shelves. So ice shelves are really difficult to constrain because radar doesn't see through water, so we can't measure the seafloor underneath ice shelves, and then we can't get sonar up here. So they're kind of a dead zone, but it's super critical for modeling the stability of our ice sheets because the bathymetry at the seafloor affects how ocean water circulates and if and how warm water is delivered near the grounding line. People use airborne gravity anomalies to infer what the seafloor looks like. So these airborne gravity campaigns are measuring changes in the mass distribution underneath the ice. So that could be changes in the topography, it could be changes in the geology or density. Again, there is a non-unique solution to this. People just kind of make a lot of assumptions to force it to have a deterministic solution and make these smooth, almost cartoonish maps of the bathymetry. My student Michael is doing the same kind of MCMC thing to randomly perturb the topography until a synthetically modeled gravity survey matches the real gravity survey. And we can use this to better map these cavities and quantify our uncertainty. So this is the mean of an ensemble that Michael generated, standard deviation, hundreds of meters. And then differences from previous estimates in that region. This is Waits Glacier, a very critical glacier in West Antarctica. So we're getting much better estimates of this environment, but also uncertainty quantification that people can then use to quantify uncertainty in their ice sheet and ocean circulation models. So this purple line is our ensemble mean, and then we have this ensemble and some uncertainty envelope. And that's from accounting for different densities and geometries, and all the possibilities that could satisfy those gravity constraints. We are currently applying this to all the other ice shelves in Antarctica in a CURE course, or a course-based undergraduate research experience that we're teaching this fall. So we've got a bunch of undergrads. We gave each of them an ice shelf, and then over the course of the semester, they're gonna apply this Markov chain Monte Carlo gravity inversion to get better bathymetric estimates along the shelves, and that'll all go into demo. So we just got started. We'll see how it goes, but I'm so far really excited about this. Yeah. So that's our cavities, the ice shelves. One really annoying thing that I haven't mentioned yet is that our radar data itself is very uncertain. That's because of something called clutter. So when you have a signal going down, that radar is going off in every direction. And we're just assuming that those return signals are coming directly below us, but they could be bouncing off stuff to the sides. And that can give us, hundreds of meters of crossover errors in our data. This is just a synthetic radargram I made for some true topography, and this is what the radargram looks like. So we could be very off. And this is something that ideally we would be accounting for when making maps of the bed topography. Right now I'm trying to do this for actually the surface topography on Mars, where we have 2 different radar systems that have been doing repeat surveys of Mars from orbit. But it's really hard to use that radar information to make these digital elevation models of Mars because of all this clutter, all the scattering and noise. But we're trying to do some sort of similar Markov chain Monte Carlo optimization where we actually use that clutter, where we can turn the noise into data and combine it with the laser measurements of the surface. So possible future application. Finally, the last little ongoing project I want to talk about is up in Svalbard, where I do field work every year. A bunch of Norwegian seismologists. We've been working on doing seismic surveys at this glacier Slackbrain. And this is a picture of me standing on the glacier looking down, and you can see this pool of water here. It's about -20 degrees, and there's this big pool of water that's coming from subglacial water flowing out from underneath the glacier. And a colleague took a sample from this and found that it had methane, so it's probably some sort of groundwater bed swamp. It's just really interesting because groundwater is incredibly difficult to image under the ice. So over the last few years, we've been doing dynamite to create these vibrations, and we can report how they travel through the ice. That subglacial geologic groundwater. It does not damage the glacier. A couple inches of snow. But yeah, it's pretty fun. 50 of these shots each year. This guy is a plastic sort of borrow him to help with detonating.
So I think first one's really exciting, and then whatever dynamite. Okay.
But yeah, so been bringing my students up here to do this.
Yeah.
There are lots of reindeer up in Svalbard, and for some reason they like to watch this. But yeah, and then I don't have a good segue into this, but I thought that it was important to mention it's out there one day. This is my student Michael in the green hat. He was filming Mission Impossible 7 Part 2. So, yeah, anyways, but speaking of Mission Impossible, my goal with this data is to do something called full waveform inversion. And basically, when you create a seismic vibration, you have, acoustic waves traveling in all directions through the earth. Some of those reflect, some of those refract. You're measuring those returns at different sensors placed along the line. And somehow you want to be able to use all of that data to solve for a bunch of unknowns about subsurface, including like ideally the porosity and permeability and density of the geology. That is not what I've done here. I've done more of a single waveform inversion for a vertical shot, but using this Markov chain monochrome framework, so far I have managed to solve a very simple problem of what is the density of the bottom layer under a glacier from a synthetic seismic image. So my goal is to use this geostatistical Markov chain monochrome framework we've developed to take all of these different types of seismic waves and all their orientations to better constrain, the more detailed geological characteristics under the ice. This kind of thing hasn't been done in glaciology yet. Again, it's been done in the oil industry. So my hope is that we can use our techniques to kind of bring this geophysical school of thought to our field. In summary, by using geostatistics with a bunch of other kind of optimization and geophysical techniques, we can give ourselves a much more robust and geophysically realistic picture of the landscape underneath the ice. That lets us learn a lot more about the hydrology, the fundamental sliding behavior of our ice sheets, and ultimately better quantify uncertainty in ice sheet behavior, sea level rise projections. I'm only getting started at UF, so we have a lot more to do in this area. I haven't really worked much beyond glaciology, but I think a lot of the things that we're doing here are probably relevant to other areas of hydrology, certainly Florida aquifer. So happy to chat about how we can transfer some of that knowledge to your domains. And then I also teach a few classes. All the numbers are probably going to change as we get improved. This one is my data science and machine learning course is a mixed Friday course. Yep. I'll be telling the screen. So thank you.
All right, we'll go to questions. I'll look at Zoom and YouTube. We have questions for Dr. Mackay from the room. You're not going to go first. Let students go first.
So have you reached out to or tried reaching out to people who work in like industry in the middle? Because you've mentioned a couple times how they use things and stuff, and I assume it's kind of like proprietary. They don't want their hush mouth and don't want
I've a couple like industry connections who've been able to like tell me kind of explain some of the math to me or algorithmically what they're doing, so I can go code that up in our own stuff, and talking with those people has been very useful. When I was doing my PhD, I was co-advised by a professor, Jeff Harris, whose group was basically funded by Chevron. So that's where I got a lot of this from. I have found the industry overlap to be very useful, even if that comes with the oil connections.
Well, I was wondering if there's like anything, like any sort of friction about that, because you're kind of using a lot of the things that were developed by the oil industry to talk about climate change. I
haven't run into any issues so far from either end. I do, I spend a lot of time with Norwegian geophysicists who mostly kind of like they're big in oil there, and I think they would love for their stuff to be used for more sustainable purposes. Like they don't want their legacy to be the destruction of the earth. They want their legacy to be like good geophysics. So from the oil industry, like certainly they seem happy to like, you know, for any opportunity to like look less bad.
Mhm.
In the scientific community, I think, you know, we're all geophysicists. We just want to do our science better. And, you know, I think we're starting to acknowledge that, you know, our little inward looking field needs to really make connections outside of our field if we want to, you know, be able to achieve our research goals. Yeah.
Can you get any information by looking at glaciers that have almost completely melted?
Yeah. So that's less my area of expertise, but there are many of my colleagues who look at deglaciated landscapes in the Arctic. I had a couple of papers where we were using deglaciated topography up in the Arctic as training images for doing geostatistical simulations of the topography underneath the ice, which was fun but very challenging because you don't exactly know how, like, if something is representative of that subglacial environment. But yeah, they do make a good analog for this stuff.
So I was wondering, you know, you spent a lot of time talking about smoothing geostatistically is bad,
Mhm.
but then there's this process of like ice scraping along the bottom, which is like an erosion, like,
Yeah.
so, I guess, why is it not smoother? Like with all of that transport back and forth, I mean, maybe like where it has been stable for years, yeah,
Yeah.
but if the process you're most interested in is the movement, why isn't it smoother?
Yeah, I mean, there are parts of the subglacial topography that are relatively smooth, especially in the big sedimentary basins. But I mean, if you think about like places that used to be glaciated, it's like Norway, Sweden, there are smooth parts, but there are also very mountainous parts. And
It's
you
just
know,
like the age of the up, it's like that
it
uplift
depends on the
is.
geology. If it's, you know, and depending on the flow regime. Some of the biggest mountains on Earth are, but then you also have big smooth. Yeah, it depends. But our geostatistical algorithms, I set them up so that we can roughness by region. So we can impose, you know, different roughnesses on different so that we can account for that non-stationary or variability in the terrain, which is very important.
So does your findings or will your findings be plugged into a larger scale improvement of kind of this subsurface, then somebody else takes a model and adds that as a hopefully a better prediction of where things are going. So it's a piece of the puzzle, but not the end of the puzzle.
Yeah, so Demogorgon is going to be an ensemble of the topographies, and then that will be fed into ice sheet models. I don't know if it'll be me doing it or somebody else. My student Nia has started taking her, you know, smaller scale simulations and putting those into ice sheet models to, you know, get case study estimates on the uncertainties. But I suspect it will be either Nia or somebody else who does the Demogorgon full ensemble runs for Antarctica.
Does anything suggest that this coarser topography or maybe higher resolution topography is going to slow things down, or is it all kind of point to a possible?
Yeah, it's really tough to say because, like, when ice sheet modelers, you know, initialize their ice sheet models, they just have a bunch of other parameters that are compensating for the smoothness of the topography. So the other thing we're kind of thinking about is that, okay, we've made our, you know, alternative topography, but we also need to fundamentally change this ice sheet initialization process that when we plug in our topography, there's not just some other parameter that
It just gets tuned down.
Yeah. So I'm writing a proposal right now on how we can like do a geologically informed basal friction coefficient inversion where we, you know, use observations for that instead of just
tuning.
Yeah, just tuning. But yeah, so you know, I think it's definitely I can't say that it's gonna slow it down. Especially because we've shown that with the rougher topography, the ice becomes rheologically weaker, so more deformable. In Nia's very preliminary ice sheet model runs for her area. She found on average it meant more retreat, but there's a lot we need to like quality control before I would stand behind that result. But I was surprised to see that for sure.
Well, let's give Dr. McKay another round of applause. Thank you very much. And please, everyone, be sure to join us next week. Next week is September 11th. We're having Dr. Mark Rains from USF. He's also currently the Chief Science Officer for the state of Florida. And he claims he's going to be talking about like surface water, groundwater interactions in Alaska. So we'll stay cold, but I think we can bug him about stuff in Florida too. So we'll see Dr. Rains next week, and thank you so much.
Yep.
See y'all next week. Cheers.
Come early if you want to see, because it's like.